All right, so we saw in the previous video how to compute the expected counts by hand and why it makes sense that we can do that given a contingency table. We're not going to be finding that by hand anymore, so that's why this is starting a new video. So to perform a test for the independence of categories, you will usually be asked the question, are the row or column variables independent? We've seen that question before when we did probability, but now we're going to be able to perform a more holistic test. So we're always going to go ahead and write the hypothesis. Remember that when we found the expected counts, we assumed that the categories, the rows and the columns, were actually independent. So that's going to remain your null hypothesis, that the rows and the column, in other words, your categorical variables, are actually independent. The alternative is that they are not independent, so therefore they are dependent. The conditions for the test are very similar because it's essentially a goodness of fit test, as we saw previously, because from the data, from the observed, we compute the expected using the independence assumption. And so for our requirements, we're still going to go ahead and just essentially focus on the fact that we need the expected counts all to be greater than 1 and no more than 20% of the expected counts are less than 5. If that holds, then we know that we can proceed with the goodness of fit test. Now, the goodness of fit test is still using a chi-square distribution, but this time the degrees of freedom is slightly different. The degrees of freedom is going to be the product of the number of rows minus 1 times the number of columns minus 1, but it'll still be a right-tailed test. Okay, so that just means that we have a bit more categories, but it's still a right tail because we're measuring the level of disagreement between the observed and the expected. And that's pretty much it. So this formula should look familiar. Again, it quantifies the amount of disagreement. Let's complete our hypothesis test. So are happiness and health related? That's the question. Notice they're asking, are they related or independent? So we're going to test to see. So I'm going to go ahead and start with my null hypothesis. I'm going to say health and happiness. So always write out the variables. Are the null hypothesis is independent. And the alternative is that they are not. All right, so we've written out our hypothesis. Now let's check the conditions of the test. Remember that if you have your data in StatCrunch, you can get the expected counts by going to stats, tables, contingency with summary. Select only the columns at the top. So that was poor, fair, good, and excellent. And the row labels are var1. Make sure that you scroll down a little bit and you select here the display that says expected count. And just for demos, I want to also show right here contribution to chi-squared. So what we're going to do is we're going to read this right here that says the expected counts are the middle number in parentheses. So here's expected counts for each entry, every cell. And you can observe that each of those is in fact bigger than 1, and there are none that are less than 5. Notice that we also have the contribution to the chi-squared. So this number, for example, 3.01, where does that come from? That comes from the formula observed minus expected squared divided by expected. So if you actually take your calculator out and you say, here's my observed, here's my expected, and subtract them, square it, and then divide by the expected, you should end up with 3.01. Okay. All right, and so once we do this, you're actually done. You need to, when we find the expected count, we actually get our test statistics. So let me go ahead and just verify here that the EI, all the expected counts, are actually greater than 1, and none are less than 5. So we meet the requirements. We can therefore go ahead and sketch our distribution. And let me actually compute the degrees of freedom here. Remember, it's row minus 1 times column minus 1. So we got to go back and count how many rows are there. So there's 1, 2, 3. There's 3 categories there for the row. The columns, that was poor, fair, good, excellent. That's 4. So this gives you 2 times 3, which is 6. Now you could compute it. I like to compute it just because it encourages us to really think about what we're doing. Or you could have just looked at the degrees of freedom as part of the output in StatCrunch as well. All right, so anyway, we got the degrees of freedom. Degrees of freedom is 6. And now we can go ahead and find our critical value. So alpha is 0.05. All right, so go ahead and find your critical value and your chi-square stat. All right, so let's fill everything in. So my critical value is 12.59. My chi-square stat and p-value, those we've already observed. 180 and less than 0.0001. And this makes sense because 180 is ridiculously large, right? Way larger than what I've got here. This goes from 0 to 12. So 180, that's more than 10 times as far away. So this is definitely lying like way the heck over here, way off to the right-hand side. So we have more than enough evidence that there is a lot of disagreement between the observed and expected. So we're going to reject the null. And the interpretation will be that we have sufficient evidence at the 5% significance level that health and happiness are related. Now, we did not need that. We did not need to know that usually when people are sick, they don't feel very good. So it's hard to feel happiness. But this is more or less the way that this works. You notice that there's really only a few changes when you're doing a test for independence, and that comes in the hypothesis. And in the degrees of freedom. I guess there is one more just to emphasize, and that was the command that we had to use. The command was stats tables contingency and we're going to select with summary. But that is more or less it. In the next example, we will work through example 5.